Hello everyone, this is Mr. Fu. I'm here to share a simple document on experimental chemistry notes. So I'll be sharing part 1 here, which is the notes for preparing students for practical examination, right? So I'd like to acknowledge the work here came mostly from the school I used to teach, 2 schools. So I combined their materials together as one and formulate a new way to classify different types of experiment. I will show you later how I classify them to help students to write a better experiment plan and some of the key points for them to take note. All right. Now, the first page is nothing unusual. This can be extracted from the O-level document on practical skills. What are the skills the students will be assessed on from planning, MMO, PDO to ACE? All right. This is also extracted from the O-level document where students will need to know what are the topics that they could be tested on in practical. Since organic chemistry is taken out this year, there will be no organic chemistry practical for O-level examination. But the skills involved could still be tested, like how to do a test, all right? But that is also covered under QA. So nothing unusual here. Some tips on practical techniques are like simple things like burette reading should be in 2 decimal places, and how much reagent should be added during QA practical, and what are the observations they should make and write down, like color change of the solution, the color of the precipitate, and the name and test of the gas. Units. What are the common units they are expected to know and use it in the questions? Significant figure. So how do they use the appropriate significant figure? And how to draw a proper data table? What are some of the main points to take note of? For example, the units can only be shown in the heading. The values of the same heading should be in the same decimal place to show the precision of the instrument used. The process data should be 1 significant figure more than the raw data. Drawing of graph, what to take note of, some of the pointers, including exemplars and non-exemplars, so that they avoid making mistake in drawing graph. All right. Line of best fit, what do you mean by line of best fit? So the line of best fit need not cut through every single point, okay? It is the best average of all the points, all right, to minimize random error. And how should the line be drawn? Sources of error questions will definitely be tested for practical exam. So what I did was a shortcut method, meaning I told them if it is on energy change involving usage of thermometer, then the standard source of error will be heat loss of surrounding. How it affects the data collected, they need to be very specific to say whether the temperature recorded is lower or higher than expected. If it's an exothermic reaction where heat is released, temperature rise, then the maximum temperature recorded will be lower than expected due to heat loss to surrounding. If it's endothermic reaction, it will be the opposite. The temperature measured is higher than expected due to heat gain from the surrounding. So they need to be aware of that because the question could be endothermic reaction. And how experiment procedures can be improved to reduce the error, like using a plastic lid to reduce heat loss, or use a styrofoam cup with higher wall to reduce acid spray and hence minimize heat loss. Okay, in part 2 of my experiment planning later, I will show you examples of prelim questions where the examiner don't want students to talk about heat loss. So what are other source of error the student can think of? For example, it could be something to do with the reaction itself, like impurities, or it could be due to the instrument not precise enough. For example, they use a measuring cylinder, so maybe they want to improve precision, a use of pipette might be better. Okay, rate of reaction always involves the use of stopwatch. So I told them if you use stopwatch in the experiment, then the common source of error will be the time lag. It's wrong to just say human reaction error because it's not specific. So they need to say how is it a human reaction error? Instead of saying human reaction error full stop, they should elaborate what source of error is that. So the time lag between adding reagents and starting stopwatch, and time lag between stopping stopwatch and observing the cross to disappear. Okay, this is a typical question on observing the cross disappearing due to the formation of the sulfur precipitate. All right. And how does it lead to inaccurate measurements, and how they can improve? The only way is to improve and cannot eliminate totally, is to repeat it for each concentration and calculate the average time to ensure reproducible results or improve or increase reliability of the results. So if it involves thermometer, if the examiner doesn't restrict the source of error, it will be something related to heat loss. If it's using of stopwatch, then it will be time lag. So what I showed here was telling them that regardless of the experiment nature, as long as it's observing something disappear, then and taking the time, then the source of error will be very similar. Yeah, this is another type of experiment that involves gas collection. So they can actually talk about the stopping of the conical flask when starting a stopwatch. So for this one, have to be very careful. It's not the same as the previous one. So if let's say gas strings really came out, where they need to use the gas strings to collect the volume of gas, then they cannot just say time lag. That is wrong. They need to talk about the problem with stopper the conical flask as starting a stopwatch, because that will result in loss of CO2 gas. And because of that, the volume of gas collected within the given duration given will be smaller than expected. So they need to be very specific, because previously, right, for this one, right, it's okay to say inaccurate measurement because you either start your stopwatch early or start your stopwatch late. But for this, it's quite clear that the stopwatch was only started, all right, when you manage to put the stopper in. But while you're trying to use a stopwatch and stopper the flask, right, some gases is lost. So the volume collected will definitely be less than the expected one. All right. Or they can mention the CO2 itself is slightly soluble and therefore the volume collected will be smaller than expected. And these are the way to improve. For example, they can they can put the calcium carbonate in a test tube, tie it with a string, and then pull the string so that you avoid lesser gas loss. Okay, this is similar. So there are different types of experiment that involve speed of reaction. Either they observe the disappearance of cross, or they use a gas string to collect the gas, or they just observe when effervescence stops. So it's similar to the disappearance of the cross, the experiment, very famous experiment using involving the formation of sulfur, right? Or just now that one is formation of the blue-black complex. Okay, this is another type of question which is about Stokio, where they determine the percentage of iron in a sample of scraped iron. So one key source error could be reducing agent. So for this type of question, right, where it's about redox, listen up, redox. For redox type of question, the key source of error is normally impurity. But you need to specify what is the impurity. The impurity is either reducing agent or oxidizing agent. So you see what is added to that substance that could contain the impurity. For example, in this case, right, the iron 2 sulfate is going to be oxidized by potassium manganate 7, something like that. So this is an oxidizing agent. So it could be that, okay, iron 2 itself is a reducing agent, so it reacts with KMnO4. But One possible key source of error could be there could be other reducing agent present in the solution itself that reacts with potassium manganate. So if there are more reducing agent, then your volume of KMnO4 will be greater, right? So when it is a reaction that is redox, right, think about reducing agent, oxidizing agent as impurity. Yeah, then work it out. For empirical formula type of question, it depends on the question itself. So you have to really understand what you have been doing and what are the possible error that could have been committed throughout the experiment procedure. One error could be, incomplete reaction. So the magnesium may not be completely reacted. So that will result in wrong calculation, and hence the empirical formula of magnesium oxide may be calculated wrongly. Or when the lid is open to ensure oxygen is reacting with the magnesium, some of the magnesium oxide could have escaped and lost. So that will also cause inaccurate calculation of the mass and hence empirical formula. Okay, this is still not very specific for number 2, because if the magnesium oxide is lost, then it will cause lesser mass. So you need to talk about how. So it depends on how you say. If you say the magnesium escape, then the magnesium mass will be actually lesser than expected. Then how would that increase or decrease the value? Think about it. All right. As for procedure improvement, right, you can talk about how you repeat experiment to take more readings to ensure reproducible results. Then for this one is again, depending on the experiment nature. Like if they ask you to decompose carbonate to obtain the CO2 gas to see how much time is taken to form the PPT in lime water like this, right? Then you have to focus on either impurities or intensity of the Bunsen burner flame. All right, because the Bunsen burner flame intensity may not be consistent and varies. That will cause inaccurate time measurement. All right, sometimes it's higher intensity, sometimes lower intensity. If it's high intensity, then will decompose faster. If it's lower, then slower. So for this, it's hard to tell whether it is faster or shorter time or longer time. Okay, the last part I'm going through is planning of experiment. This is something I came out with myself, the classification. So if you don't agree, then yeah, it's just my own way of interpreting to make it easier for students to write down their plan. All right. So the first step is to come up with this method called the MMRDDC method, stating the reaction and control variable, measurement, what is the dependent variable to be measured, and repeat if necessary by changing the independent variable, diagram if necessary, and if it can improve clarity of the experiment procedure, data analysis and processing, and conclusion. Okay, marks are given for each component. So what I did was I actually classified into 2 types, type A and type B. This is something new. You have never seen this before. It's something I came up with myself after I did a few rounds of teaching over the years. So type A will be a plan that involves repeating experiment by changing the independent variable. All right, so I have an example. For example, speed of reaction, where you need to change variables like temperature, concentration, or type of catalyst. That is type A, because you need to change the independent variable and repeat it. Okay, type B is a type that you don't need to repeat. You just need to carry out the experiment, plan the experiment, and it's a linear type. So it's just one direction. There's no need to repeat. There's no need to go back to step 1 or 2 and do over again with another independent variable. No need. Okay, for example, like separation, preparation of salts, calculate required quantity like percentage yield, purity, etc., or empirical formula. So this is an example of type A experiment I taken from my previous school, is on the effectiveness of different type of catalysts on the decomposition of hydrogen peroxide. So I actually break down to different parts, like variable state, what is it? Yep. And procedure. These are some of the information I tell my students, like how you must number your steps, start each step with an action verb, be clear and specific. If the operator used, you need to specify the size and the quantity. All right. So a shortcut is to just tell them, okay, if it's a catalyst, then you don't need such a big mass. Maybe 0.1 gram will do. If it's a reactant, then 1.0 gram maybe. If they say if it's 1 decimal place, put there about 1.0 gram, because the electronic balance can measure up to 2 decimal place. If they want specific mass, then have to say 1.00 gram, take out the word about. All right. As for volume or solution, it would be good if they can have like maybe a range of 10 to 50 cm3. All right. Measuring cylinder can measure up to 1 decimal place depending on the size. If it's 10 cm3, 5.0 should be not be a problem. So it depends on the measuring cylinder they use. If it's burette, have to be 2 decimal place. Pipette is 25.0 centimeter cube standard that normally used in the lab, although they are 20.0 centimeter cube and 10.0 centimeter cube pipette also lah. To let them know they exist as well. Yeah. So this is an example. So to mention safety aspect, like they should wear safety goggles and gloves when handling oxidizing substances. All right. Now, this is one example. So what I thought then is for procedure, right? It's very straightforward. The technique is called measure A, measure B, add them together and measure. And maybe you need to repeat. So I repeat, measure A, measure B, add, measure. That is the technique. Measure A, measure B, because normally questions would be substance A and substance B react together. So you need to measure A, measure B, add them, then measure. So the measuring part could be either measure the time taken or the temperature, something like that. All right, so add them and then start the stopwatch as shown in the diagram. Diagram I show later, and stop when a certain volume is collected. Specify what is the volume. Repeat. Okay, this is what I told them. If the experiment nature involve time measurement, it's a planning experiment where the student get more time. Because in their usual practical, because lack of time, they cannot repeat for experiment involving time, no time. So, but in planning, they can do so. So I expect them to write down the repeat step. So for step 5, they need to repeat 1 to 5 twice. It's important to state the number because they can just simply write this as shortcut. They don't have to say repeat, they just have to repeat the number of steps so that the experimental can refer easily. Okay, so repeat twice and calculate average time, and then repeat with other variables. This is how you can phrase it. All right. So only for time measurement, I expect them to take at least 2 more readings and calculate average time. That is the correct way. So this is the setup. So there are different ways of doing it. For experiment planning, there's no fixed answer. So, so teacher has to look at it and see if it's appropriate and makes sense, and do not just based on the teacher model answer. There will be more than one possibility for sure. All right. Yep. Data table it is required, okay. So that's for type A where you need to repeat experiment. For type B, it's just straightforward linear. So this is one type where you need to do separation and calculate the mass or percentage mass, whatever. So this one I use the, I talk about the method measurement diagram. So you see, measure, then you, for this, there's only one substance to measure. So basically, you measure the mass of the substance, including the impurities, heat them, then the data analysis part will be more important because you need to talk about how you actually calculate the percentage mass of the zinc using the mass law. So carbon dioxide form escape, and then you can actually use the mass loss, which is carbon dioxide, divide by the molar mass, get the mole, and get the mole of zinc carbonate and relate that to the mole of zinc, calculate its mass, and then divide over the initial mass to get the percentage mass of zinc. It's quite easy. So what I did was I also provide for students, some examples of type A. How do you phrase it? So I give them the template, method, measurement, repeat, diagram, data analysis, conclusion. All right. So see, measure, measure, add, measure. The steps are very standard and repeat if necessary, if it's a type A question. Diagram if it's helpful. Data analysis part depending, some like if it's more concept related, percentage year, purity, composition, then a bit long lah. But if it's something like this, it's quite straightforward. It's just comparing the average time taken for the 3 experiments. And then conclusion is important. You need to talk about if the time taken with either adding this is better, then what is the conclusion? Okay, so they need to end off with a conclusion. So this is another example of reactivity or method, which I will not go through it because it's very similar to what was done. Then I give them one more sample on comparing the strength of acid. So if it involves comparing and repeating, right, meaning you need to have different independent variable, that is type A. That's what I mean. I'm not talking about repeating if it's time. No. I'm saying type A is a type of planning where they have different independent variable and it requires them to repeat with different independent variable. Type B is something like linear, straightforward. You just need to measure and calculate. That's it. Yeah, actually, it's more straightforward for type B. I feel that personally. Type A is a bit troublesome and tedious and more things to write. Type B is more straightforward. They just go straight to the point. Yeah. Type B, like this sample 2, right? For example, it's really like a preparation or sort separation question. Yeah. So some of the exam question could be like that. Yeah. Then you have titration type of questions where they need to describe the procedure. So it's really like sort preparation. Yeah. Then the data analysis part will be more tedious for questions that involve you to calculate certain percentage of volume or concentration, etc. Okay. So that's it. This is for part 1 only. I'm still doing part 2. I'm so sorry I cannot give you everything if you ask for it because it's copyrighted. But what I can give is maybe part of it. Maybe like my description of type A and type B. Yeah, the rest of it I think is quite straightforward. Students should already know all the pointers to take note for practical chemistry. Yeah, so I hope this document is useful. And yeah, please give a like and subscribe to my channel if you like it. I really appreciate that if you can give a like and subscribe if you have any Google account. So thank you, because I will be uploading more and more videos on experiment techniques, as well as some of the, I may be uploading videos on how to do experiment techniques, the real video from the lab, as well as how to make lessons more interesting using different real life applications. So that's it. Thank you for your time. Bye-bye.